Computers are revolutionizing our lives, performing tasks unimaginable only decades ago. This was made possible by a long series of innovations. But there's one foundational invention that almost everything else relies upon: the transistor. So what is that? And how does such a device enable all the amazing things computers can do? Well, instead of electrodes, it uses a semiconductor like silicon, treated with different elements to create an electron-emitting.
Transistors are very simple components. They are basically electronic switches. When we apply current to one of its terminals, a transistor lets electricity pass through. But how can this simple behavior make computers possible? In today's video, we are going to learn how transistors can be used to achieve more complex tasks, like doing math and even interpreting instructions. A single transistor typically has three terminals: a collector, an emitter, and a base. In a circuit, it can act as an insulator, preventing electricity from flowing between the collector and emitter terminals. But if we apply a small current to the base terminal, it acts as a conductor, allowing electricity to flow. Essentially, a transistor can be seen as a switch, but instead of mechanical movement, it operates by using electrical signals. In this example circuit, we are using a transistor to turn on and off an LED. By utilizing the base terminal as an input and the emitter terminal as an output signal, we can mimic the input signal with a switch and visually represent the output signal with the LED. Let's dub this a simple gate. In a simple gate, when the input is 0, the output is 0. When the input is 1, the output is 1. Now, let's tweak things a bit. Here, when the input is 0, the LED is on due to the way it is arranged within the circuit. But pay attention to this. Setting the input to 1 causes the LED to turn off, indicating to us the output is a 0. This setup is commonly referred to as an inverter or a NOT gate. This may seem a bit confusing. If two transistors are connected in series, when both inputs are 0, the output will be 0 because both transistors act as insulators. Similarly, if either input is 0, the output will be 0. The only way to obtain a 1 in the output is by having both transistors act as conductors, which happens when both inputs are set to 1. This is where we begin to apply a powerful concept called abstraction. Instead of focusing on the individual transistors in the circuit, we can abstract this into a white box, a box that consistently outputs a specific value based on two given inputs. This is known as an AND gate. An AND gate outputs a value of 1 if and only if both inputs are 1. Otherwise, the output will be 0. If we connect the transistors in parallel, when both transistors act as insulators, electricity cannot flow. But in this setup, having any transistor acting as conductor is enough to allow electricity to flow. So in this arrangement, to get an output of 1 is not strictly necessary to set both inputs to 1. Once more, we can abstract this circuit into a box, known as an OR gate. An OR gate outputs a value of 0, if and only if both inputs are 0. Otherwise, it outputs a value of 1. These circuits, known as logic gates, are so fundamental that instead of representing them with boxes, each one is assigned a dedicated symbol. Notice that since inputs and outputs are electrical signals, we can connect the output of one logic gate to the input of another. This allows us to combine logic gates to achieve even more complex behavior. For example, if we desire this particular behavior, we can combine logic gates accordingly to achieve it. This is where we begin to see the power of abstractions. While this setup is ultimately composed of transistors, it's much simpler to understand what's happening by thinking in terms of logic gates. This circuit is known as an XOR gate, and it is also very important in computer science, so it has its own symbol. And now that we understand what logic gates are, let's use them to create more useful things.